Hi, this is Paul and I've got a new video to show you, and I'm calling this video DNA Spider 1. Okay, let's start this by showing you the size 6 Dodeca and Icosa vector system. I'll spin it around back and forth so that you can see the vectors better. And you can see that they're all different colors. Now each of these colors shows a different orientation. This is very important. The color system gives you order because each of the vectors have been given a different color. Now the position of these vectors can be copied and moved and linked together, but they cannot be rotated. They are kept in the same orientation. I've shown this vector system for quite a few years now, and I'm showing perfect order. But this type of order has never been mentioned by any academic. In the last 50 years, the focus has always been on chaos. In front, you can see on the Dodeca a red and yellow vector. I'm going to just use this vector, and we can hide the Dodeca and the rest of the vectors. Now we can use the red and yellow vector as a rotational axis for the Icosa. Now I'd like you to focus on the green and purple vectors. Those two green and purple vectors can be used as diagonals, and we can make a Phi-rectangle. Now what I'm showing is a size 6 Phi-rectangle. Now we'll just show that rectangle and the diagonals. I go into detail on these rectangles in my earlier videos, and I give all the measurements. Now in the center you can see that I show an icosahedron. The icosahedron would give a size 1 rectangle, but I'm going to show 4 size 3 rectangles. Now these can be the centers of more icosahedrons, but I'm going to change them to white balls, because I think they basically like vertices, but they can keep growing from every one of these vertices. So now we can hide the size 3 rectangles. And now we are looking at something a lot cleaner. Okay, for this, I think we'll just show the Icosa. And I think I'll make it a little bit bigger. And now we can hide the Icosa outline and just show the vectors. Now if you look, you can see that the orange, green and purple are bunched together more or less on the same plane. We'll hide the rest of the vectors, and you can see then that we can rotate that rectangle around to a new pair of diagonals. So you can see that this rectangle uses the orange and green diagonals. And this rectangle can be rotated again at 120 degrees, and it'll give us the orange and purple. Okay, so when we put these 3 rectangles together, we get another real interesting shape. I don't know the name of this shape offhand, but maybe some scholar can take a look at it and maybe write a thesis about it. That's if he's allowed to work and stray away from chaos. It seems that academics don't have the slightest interest in 3D geometry. Okay, let's move to a new scene. And I'm going to show this copying 5 of these rectangles along the purple vector. Now for this we don't need the green vectors, and we can chop the purple vector at the center of the 2 end rectangles. We can hide the rectangles and we can make the balls a little bit bigger. Okay, so we've got the first 17 ball purple vector. So now we can give it another 17 ball green vector also. And we can give it an orange vector. And turn these 3 around a bit and give it a blue vector. And then we can give it a cyan vector. And we have 1 more vector to go, and that will be a red vector. Okay, so now I've showed you how to put a DNA spider together. If you looked at my earlier video about the nucleosome, I showed a hexagon spiral going together using 9 ball vectors. I was thinking about the chaos butterfly. It got famous by flapping its wings. But what about the spider? She can build a web in 3D geometry of perfect order. I don't see any chaos in her work. It must be a she because she's so beautiful. And I think she knows her way around a DNA string. The spider is rotating around the red and yellow vector. Now this vector is one of the 10-20 vectors of the dodeca. Now this vector indicates the rotational axis of the DNA going around a nucleosome. So I think it's a good idea to use this one vector to show the axis. Okay, for the next step, I think we'll put the spider in the top view. I'm going to hide the white balls for the spider vectors. Actually, they're still there, but I'm hiding them. Okay, watch this spider when she moves out on the purple leg or vector. Now earlier I showed that the purple and green was my first Phi-rectangle I showed you. So the spider can start by moving down the green leg. And look, she's just laid the first track, the green track with 9 balls. And now the little spider can keep repeating this operation. And one of its legs will always keep the same distance from the center of the little white cube outline that I show as a center point. I made this little anim in the perspective view so that you can see the spiral going around much easier. Now I show 12 vectors in this spiral. Now this matches up with the 12 vectors I showed for the spiral of a nucleosome that I showed in my last video. And I showed that these 9 ball assemblies were given perfect 3-dimensional rung assemblies for B-type DNA. I'll show you the swirls again from the previous video. I showed that the nucleosome could work out in perfect geometry. Nobody's made a comment so far, but the academics can talk a glass eye to sleep when the subject is chaos. Oh man, I can get carried away on that stuff. So let's get back to the little spider again. So I think we'll send her back to base camp and she can eat up a track on the way back. Now we're going to move further ahead. I've made an anim starting in the front view. And this is going to make a spiral from the center going downways. Now in the geometry of DNA, I find that you cannot make a spiral bend on an acute angle. That means under 90 degrees. It's got to be an obtuse angle. And back to the spider, we've now finished making the spiral with 12 9-ball sections. Now we'll take the spider back to the center again and leave them sections alone. Now as this spider is going back, you see that it doesn't turn at all. It's locked in rotation. This is a very important feature and you shouldn't rotate the spider. Now if you keep watching this spider, she's going to start making another nucleosome, going upwards this time. Now if you study the geometry, you can see that she starts on the orange vector instead of a green vector, but all the vectors are matching up. I think researchers are going to find that they can't do away with this spider. And she's going to prove very, very useful in 3-dimensional work. And just because she hasn't got any letters behind her name, I don't think anybody should look down their nose at the geometry that she can do. Now notice between each 9-ball vector we get a step, and it's a red and yellow step. That comes from the red and yellow vector of the dodeca, because you can see that these 2 nucleosomes are rotating around the red and yellow vector of the dodeca as a center axis. As I show earlier in the video, the dodeca has got vectors coming off every vertex, 20 vectors, or you can call them 10 if they go straight through. So in the research for nucleosomes, I think these vectors are going to get results that are accurate. I don't think scholars can tell an artist how to put something together without 3D geometry and make it very accurate. And some say that they can duplicate the human brain when they solve the chaos theory, because 3D geometry is too trivial to work with. Oh well, I hope you don't find my little spider too trivial. So this is Paul saying thank you very much for watching my video.